Here we are, it's the physics video lecture. Physics 203, video lecture 24. We are talking about fluid mechanics. It's a pretty big task, and we're trying to get through a logical, thorough set of concepts. And it's a huge subject, and we only have a few lectures. Nonetheless, this will work. So let me just encourage you again to take really good notes, space them, leave a lot of space, fill in all the missing things. And our goal here on these next 3 or 4 lectures is just to get all of the missing steps. So instead of homework per se, we'll just keep doing the notes, and I myself will pretty much do everything. Make sure you're able to get all the missing steps. Okay, good. So without further ado, let's remind ourselves where we were. We had the Euler equations, so we're working on fluids, continuum mechanics. We had the following equations. We had continuity, which is to say conservation of mass, and that equation is d rho dt plus divergence rho times v is equal to 0. V is the velocity vector field. Then Newton's law, so I'm even going to write here Newton, actually, no, I'm going to write Euler. Euler's equation comes from Newton's law, as I showed last time. dv dt v dot grad applied to v equals minus 1 over rho gradient of p. And I'm going to go ahead and include the external field in there. There's a vector here. And we'll see later, this external field can be incorporated into the pressure, but for us, external gravitational field. That's Euler's equation. And we also had entropy conservation, or entropy being constant, not entropy conservation, entropy being constant because there's no dissipation. This is an ideal fluid. Ideal. Fluid without friction. And then you had ds dt plus, what's the formulation here? V dot gradient s. That was just a chain rule, really. Gradient s equals 0. We're not actually going to use this one now. We'll make use of it when we talk about waves. Okay. And I said something about the boundary conditions. That's what I ended with. And that needs a little discussion as well. So for the boundary conditions, we say that at a fixed surface, v dot n hat, which is the surface normal of the surface, is equal to 0. Okay. And what that is requiring, what that means is that the perpendicular component of the velocity vanishes, because obviously some velocity into, say, the board has to stop at the board. Now this is worth belaboring a moment. Okay. So for us, those are our conditions right now. But the very important note, this is for the ideal fluid. Okay? A real fluid actually has a stricter boundary condition. A real fluid has a condition that the velocity, all components, equals 0 at a fixed boundary. And what that means is the tangential and the normal component vanishes for a real fluid. you can kind of see this if you try to blow fine dust off of a surface with your breath. You can't do it. Really fine dust won't move under a wind because if it's really, really fine, because the tangential and the normal components vanish. So yeah, we're going to add that in the note here. Tangential and normal components vanish. So adding to this here, this means the parallel and the perpendicular components vanish. And this then gets into highly technical terrain, because this boundary condition here that I have written down here in blue for a real fluid cannot be satisfied by Euler's equation. Euler's equation actually has to have a friction term, we could call it, dissipation term, added to it in order to be able to solve these boundary conditions. So things get pretty technical. Nonetheless, we're not going to have to worry about that, but this is a important part, important fact. Good. So what we're going to do next is a couple of applications. And we're going to start with a really simple application, namely a hydrostatic application. So we'll call this hydrostatics. These are things that you had in your lower division class. But experience shows a lot of students don't even remember that, or maybe didn't even have it, okay? The chapter on fluid mechanics, but I still recommend that you look at the chapter on fluid mechanics in your lower division undergrad book, because it has a lot of interesting stuff, but we'll cover some of that. So hydrostatics, well, if the fluid isn't moving, V is 0, and you're actually just looking at the right side of Euler's equation. So hydrostatics, V is identically equal to 0. And then I'll write here from Euler's equation, we would have, we can go here, gradient P equals rho times G. And then if G is pointing down, and if G equals minus GK hat, okay, so it's pointing down, there's Z-axis, G's pointing down. Then what do we have here? Then we have dP dx equals 0, dP dy equals 0, dP dz is equal to minus rho G, and just concentrating on this one here, P is equal to P0 minus rho GZ. So that's the good old pressure depth formula that you've probably seen before. So as an example of this, we could have a beaker of water. There's a z-axis. We'll call that 0. The origin is 0 of the z-axis. Beaker of fluid, and then you have that pressure depth formula. And I can also write or P equals P0 plus rho GH, where H is the depth under the surface. That's the way it's often in our books, okay? So one or the other, H is equal to the depth. Very often, P sub 0 is the atmospheric pressure, and you're going under a fluid, and you see that you need that gravitational acceleration there in order to have that increasing pressure Pressure increases with depth. Okay. Good, so the pressure depth formula, I'll even write this here. Pressure versus depth formula. Okay, our next application, we're going to talk about Archimedes Principle. That, of course, is very important. In fact, there are three ways I can discuss Archimedes' principle. Let's see how we want to tackle this. I may do all three of them, as a matter of fact. So let's call this force on a submerged body. Force on a submerged body. So there's our beaker, there's our submerged body, and the pressure increases with depth, as we see from here. So there's a greater pressure. I'll do some red arrows. You know, we have D force is equal to pressure minus pressure n hat D area. So on these parallel sides, the forces are equal, but there's going to be a greater force pushing up than there is pushing down. Okay. So the net force, and this is actually going to be the buoyancy force, is going to be, let me go ahead and label this 1 and this 2. It's going to be P sub 1 times area pushing up minus P sub 2 times area, which is pushing down, and the sides are not doing anything. And then we have this, either of these two formulations. So we can factor out the area, get the P sub 1, P0 minus rho G Z1. Okay, minus P0 minus rho G Z2. Bunch of parentheses there. Okay, so let's just look at this. P0 minus P0. Okay, so minus rho G Z1 minus negative, so we have rho G Z2. So what we end up with is A, the P0s are gone, A times, here I'll factor it out, Z2 minus Z1, and then the common, what's left is rho times G. So what's going on here? Well, let's write it this way, rho times A times Z2 minus Z1 times G, and we'll place some parentheses here. So what I have in the red parentheses is the volume, area times the difference in these two depths, which is the height of our object. And this is the famous Archimedes principle. The density of the surrounding fluid times this volume, right? That is a volume. So density times volume is mass. So this is the mass of the displaced fluid times G. Okay, having said that, I'll just use this part of the board. So buoyancy force is equal to rho fluid, volume of fluid displaced, that's B, times G, rho VG. Well, that is mass times gravity, the mass of the displaced fluid times G. That's the weight of the displaced fluid. Weight of the displaced fluid. Okay, I'll put an exclamation point. That, of course, is something you should know, Archimedes Principle. So let's even put that here, Archimedes Principle. Archimedes, okay. So the buoyancy force is equal to the weight of the displaced fluid. Okay, we want to talk about it in terms of our formalism. And then I'll show you well, that was in terms of the formalism, but actually in terms of that integral, which is kind of a useful exercise as well. So my second of 3 proofs. All right, let's see here. Yeah, so the second one, again, Archimedes. So here we've got our beaker of water, and this time it's just some arbitrary volume. Okay. Here, up there I had some kind of cube, right? So arbitrary volume. That is submerged right here. And then the force on it, we'll use that integral we had last time. So we're going to have the buoyancy force dotted into the ith unit vector, x, y, or z unit vector, okay? That's the buoyancy force ith component, and that is minus the integral p x I hat. So I had this last time, but this is worth repeating. The area over the boundary of that volume. So now we can use the divergence theorem. So that would be the divergence of p x I hat d volume over that volume, and the divergence of a scalar times a vector. Okay, that's where that gradient's going to come in again. And yeah, I had that identity up on the board last time. So I'm just going to go to what we get, negative over V0, negative rho G d volume. And this is the one for x I hat is equal to k hat, which we're calling the z direction here, okay? If you do it for the other two vectors, it's 0, okay, because our pressure gradient is in the z direction. Okay, so the other two integrals would be 0, and this here, I'm going to pull out the rho g, and we'll have the volume. Okay, so I'm going to leave this actually as the proof. Okay, you can draw the last step. Rho g, integral volume, just the way we had before. Rho fluid g, volume displaced. Yeah, so check this one out as well again. Check the identity for divergence of a scalar times a vector. And we had that last time. Good, so that is the more formal proof, but interestingly there is a proof almost by pure thought. And I'll even discuss that one right now. So I'll just call this the note the third proof goes like this. You just imagine this arbitrary volume that's submerged just to be the water itself that's been encased in some either hypothetical or real thin film, okay? And since you're looking at water in equilibrium, then all of the mass of the water in this arbitrary volume has a weight, okay? Its weight is located at the center of mass, and that's the mass of the fluid times G, okay? And why isn't it falling? Because all of these pressure times D area are pushing, and that net force is retaining the placement of the water in place, and that's the buoyancy force. Okay. So actually what you need for that proof that I just kind of stated in three sentences is Pascal's principle. You're assuming Pascal's principle, you're assuming that these forces are perpendicular to the surface and so forth. Okay. But good, Archimedes principle, very important, and I'll just give a really useful and interesting application, kind of the classic application. Now that we have that, three different ways. I'll just retain this picture here. Well, no, we'll just, so the original legendary application is finding the density of some mystery material, and the Archimedes was supposed to find out whether crown maybe or some craftsman object was pure gold or had been debased with too much silver or something. So you needed the density of an object. Because the density of gold is 19 times the density of water, the density of lead is only 11 times the density of water. So if you took a little lead ball from a fishing store, a sinker, and plated it with gold, you shouldn't be able to be fooled by that. Other people maybe, but physicists no. So let me draw the situation here once again, and this is actually a lab you guys may have done. You have some object, some mystery object here, and you're asking what the forces are on it. You have mg, its weight. There is a buoyancy force, and there is a tension in the string. Okay. And what we're going to do is just write down buoyancy plus tension minus mg equals 0. Now the mass you can get by weighing the thing in air. Okay, so you know what the mass is, you already weighed it. Now you're holding it on thread, submerged, and the tension is what you can measure there. So we have density of the fluid, which is water, volume displaced G plus T minus mg is equal to 0. We're just going to solve for the volume. So this is the volume of our object, and that's its weight in air minus its weight when it's submerged in water divided by the density of the water times G. So now you have the volume. This could be a really small, say it's a gold ring or something. It could be a very small object. You've done two careful measurements. You now have the volume of that object. Therefore, the density of the object is just the mass divided by the volume, and then you can check that off against the table of values and see what it really is. So density here is, of course, the fluid that you're submerged in, and density here is the object that was submerged. And so if the object comes out with a much lower density than, say, the gold it was supposed to be made of, then you caught the cheater. Good, so that's the classic Archimedes example. And having done that, let's see where we're going next. Okay. Ah, yes, excellent. So next I want to do an example of dynamics. So the full dynamics of the Euler equation. We'll erase this. In fact, this is a dynamical example for an incompressible fluid. So our next example, Euler equation for an incompressible fluid. Think water under ordinary circumstances. And what we're going to look at is a rotating fluid. We can call it rotating bucket. The idea is if you have a bucket or tub of fluid and you have it rotating, it eventually will be rotating just with the angular velocity of the rotation of the bucket. Okay? So that's what we mean by the rotating bucket. Good, let's write down the Euler equation. Since it's incompressible, we have the divergence of V is equal to 0. And we have the Euler equation, which was dV dt V dot gradient V equals minus 1 over rho gradient P plus gravitation effect. Okay, but this is a nice example in that we're going to guess the solution, because really the fluid is rotating like a rigid body. That's the idea. So fluid rotating like a rigid body, which is what happens if you wait long enough and you have the fluid rotating. And what else happens is that the surface of the fluid will take on an interesting paraboloid shape. So, because of that, we actually can state what the answer is. So V is just going to be omega, let's see what letter I'm choosing. Yeah, omega, I'm using capital Omega cross R with this omega is equal to 0, 0, omega. Okay, so the z-axis, rotating on the z-axis. And R is just x, y, z. And that gives us a velocity vector. This is the first and last time you just get to guess your answer and get it right. Okay, so that's just x, y, and z. So I'll go ahead and write that out. 0, 0, omega, cross product, x, y, z. And we're just going to get 2. And this is just your uniform circular motion result, really. Omega y and omega x, 0. Okay, Good old counterclockwise rotation. So there's the velocity. Now what we're going to do is check that the divergence is 0, and then we'll see what happens with Euler's equation. And of course, the divergence is trivially 0 because the v sub x, the derivative with respect to x of v sub x is trivially 0, and same for v sub y. So we see the divergence vanishes. So that's a good start. So divergence of v is equal to d dx, v sub x plus d dy, v sub y, that's 0. And the other thing is, well, let's just do it one step, one at a time. There's no explicit time dependence of v, right? So that's 0. And now we have this thing right here. We know because of the, well, I didn't state it, but we have a rotating, let's do this. Here's our x, y, and z, and we have something that's rotating like a cylinder there, okay? Because that way we know the pressure gradients and the z is only in z direction. So let's see what we get there. So we're going to write down Euler's equation. And that will be Vx d over dx plus Vy partial vector y plus Vz dz applied to this vector minus omega y, omega x, 0. So what do we get? Vx d over dx will just give us a 0. Vy d over dy will give us Vy times negative omega. Vz is 0. Good. So once again, Vx d over dx on this omega x here is Vx omega. And Vy d over dy, of course, 0. Vz d over dz is 0. And then the third one is trivially 0. So this is minus Vy, which is omega x times omega. So this is minus omega squared x. Ditto here, Vx omega, that's minus omega y times omega, so minus omega squared y, and 0. So this is the left side of Euler's equation, and this vector is equal to 1 over rho gradient p plus g. So we're going to have gradient p plus g. Where's the c here? Good, good. Okay. That was the one. That's going to be in the z column. So 1 over rho gradient p is minus 1 over rho dp dx minus 1 over rho dp dy, and then negative g down here. I could write negative 1 over rho dp dz, and the g is pointing down, minus g. Okay. So this is our differential equation, and what we're going to use it for is to solve for the pressure, and then we're going to evaluate on the surface of our rotating body. This can all go. So the last equality there is our differential equation. And for the first line, working right under here, the minus signs cancel, so we get dp dx is equal to rho squared omega, rho omega squared x. Omega squared x. Same thing for dp dy, rho omega squared y. Rho omega squared y. And dp dz. We've got a 0, so that's just going to be minus rho times g. Okay, so now we're going to get the pressure as a function of all three variables. And you can see we're just going to have an x squared over 2, y squared over 2, rho gz. So P is equal to 1/2 rho omega squared. First two equations, x squared plus y squared minus rho, minus rho gz plus some constant. So now let's go ahead and put a box around that. So there's the pressure in the fluid, and what we're going to do is evaluate it at the surface. Okay. At the surface, P is equal to constant, say the atmospheric pressure, and therefore we can get z as a function of x and y. This is a great result. Z is equal to, you'll notice the rho is going to cancel, is going to equal omega squared over 2g x squared plus y squared. And that gives us the shape of the surface. A rotating fluid has a paraboloid shape. Anything else to say about that? Yeah, all right. Shape of the surface. Paraboloid. So if you have a big piece of molten glass and you want to turn it into a telescope mirror, you have it rotating at a certain rate, and you can control the curvature of it. It starts out as a fluid that's rotating, and then you keep it rotating, and it'll solidify. It'll turn into a solid with this shape here. So that's a pretty good application. I saw a little article once where they're talking about taking a dish of mercury and having it rotate and therefore get a perfect paraboloid mirroring surface as well. Okay, shape of the surface paraboloid. That's a good application. Let's see where we are time-wise. Okay, excellent. Okay, one thing I want to do, very important now, I want to go back to this rotating fluid and investigate it a little bit more. Okay. Okay, so returning to V is equal to minus omega y omega x 0 for the, what we'll just call the rotating bucket. What we want to look at is the curl. Okay, so the curl is an important vector analysis, vector analytic operation. And this is probably the original place where the curl was even discussed and debated and studied. Okay. So let's calculate curl. So we're looking at curl of V. It's only going to have a Z component to omega. Okay, so that's the curl. Because for the x component, you've got dy dz. For the z component, dy dx. So only for the only for the z component do you get a non-zero contribution. So if you're looking at your rotating bucket here, here's x, y, and z. You've got this rotating object. You can see the curl is parallel to omega itself, to the angular velocity to omega, and this gives you, and let's go ahead and do a top view. So if you're looking down on it, we'll just say xy like this. Okay, you've got that rotation, and then the curl, actually the name curl is sometimes referred to as the rotation over in the European area. The operation is referred to as rotation, because you get the really intuitive version of what the curl means when you're actually talking about a rotating fluid. Okay. Any little object in here is itself going to rotate because the fluid is rotating. Good, so we have that, but there are some related examples where the curl vanishes. Now I was going to assign this. Maybe I'll do it with you guys. So we've got the curl, that's very important. And what Stokes' law, what Stokes' integral theorem has to say is also really important in this regard. Good, we've got the side view and the top view. So Stokes' integral theorem, what does Stokes' integral theorem say? Integral of the curl of V dot n hat dA for an area is equal to the integral of v dot dl for the boundary of that area, closed integral. Okay. So v dot dl would just be equal to, so let's do the right side here. Yeah, since it's just the tangential velocity, v dot dl would be omega r for, okay, let's do dA of a circle, right? We're doing a circle. So omega r would be the radius times 2 pi r. And over here, the curl of the v, which is just 2 omega, okay, times the surface area of the little circle of radius r would be pi r squared. Pi r squared omega, okay. So Stokes' theorem, you also see what's going on. So Stokes' theorem, let's go ahead and make sure we write for circle of radius r. Circle of radius of r. Okay, so that pans out. Stokes' theorem. Now there's one example I want to get to. I have to locate this thing now. Okay, so here's what we're going to consider next. So what we're going to do is take this same rotating bucket idea, except we're going to multiply it by a power of r. So we're going to take the same vector omega, but cross it into r to the n vector r. And now we're going to make sure we specify, because it's a rotating object, okay? The idea is rotating, so where this r is just root x squared plus y squared, okay? We're not worried about the z component because it's just rotating, with the axial symmetry. So there's that. So we want to find the curl of this v. Okay. You know what? I'm going to leave that for you guys to do. It'd be best if you just include it in your notes. I'll tell you what the answer is. In your notes. Okay, so we have r to the n times r here. So when n is equal to 0, we already know the answer because that's what we just found, okay? R to the zeros is 1 curl bar, okay? But n can take on any integer value, okay? N can take on any integer value. So here's what happens. Oh yeah, and I even have what I just said, but explicitly x, y, and 0, okay? That's a 0. Okay, so here's what happens. Is they do a little bit of chain rule and what have you. No big deal. Is equal omega 2 plus n, got a r to the n k hat. So there's the answer. Show this. And just leave a few lines in your notes and you can show that, okay? So I want to talk about what the significance of that is. when n is equal to 0, it's just 2 omega the way we saw here before. And, you know, it looks complicated when n's this, that, or the other, but what about when n is equal to negative 2? Okay. When n is equal to negative 2, this curl vanishes. Even though this is an omega cross r vector over r squared, something that has the magnitude of 1 over r. So a rotating, now we can talk about vortices, a vortex that has this velocity distribution, velocity field, has 0 curl. Okay. 0 curl away from r is equal to 0. But if you apply Stokes' law, and you know I'll leave that for you guys to do it in your notes again. So, evaluate Stokes' theorem, and especially for n equals -2. There you're going to get something very interesting, because this side of the integral is going to be 0. Okay, this one. Okay. But this side is not going to be 0. And that's important. That's something that you have. This thing is then referred to as a vortex filament, and plays a role in not only in fluid mechanics, but in electricity and magnetism too. So yeah, this is a really interesting application. We're not going to pursue it, but it's good for us for 2 reasons. It makes some connection to other branches of theoretical physics. It shows us that there are curl-free fluid flows. Okay, fluid flows with a curl equals 0 also exist, and they're very important. So good. Okay, that's mainly what I wanted to say today. Okay, yeah, so here you're going to, in fact, if you just thoroughly go over what we've done here, you'll see some really interesting stuff. Okay, nice review of Stokes' theorem. Here it checks out. N equals -2, you're going to have a little surprise. That's interesting. Okay, let's see where else we're going to take this. And like I said, leave yourself enough room. You can do these things, put them in your notes. You don't have to do them twice, right? Just leave them in your room in your notes. Yeah, what I want to do next is make my way up to Bernoulli's equation. Okay, good. So next, fluid flows for which the curl of V equals 0. Part of the reason for this was just to give a concrete proof of concept that such a thing arises. There would be more trivial examples. A constant flow that is just uniformly flowing everywhere in the same direction would of course have a vanishing curl as well. But that would be a little bit too much of a trivial example. So this is what we're going to do next. Actually, I'm going to leave it here. Like I said, go ahead and play around with these examples. And this way we will, so most root curl equals 0, and also Bernoulli's equation. That's where we're going to head next. In fact, you might want to look up Bernoulli's equation in your undergrad text. But yeah, I'll do a decent little treatment of that as well. Okay, good. See you guys later.